We now want to investigate how to find the general solution to a homogeneous second-order differential equation whose characteristic equation has a repeated root. So let's just start by taking a look at this example, 4y double prime plus 4y prime plus y equals 0, to even see what that means. So I'm going to start by writing down the characteristic equation, 4r squared plus 4r plus 1 equals 0. And when I go to factor this, we get 2r plus 1 times 2r plus 1 equals 0. And so what we get from this is r equals negative 1/2. And that's the only solution here. So we say it's repeated because there's two factors that look exactly the same. So those factors are what's actually repeated in this factored form. And so make a note of this, repeated factor. So we call this a repeated root. All right, so we want to figure out what our two linearly independent solutions are. So what we do when we have a repeated root is we have our first linearly independent solution of e to the negative 1/2 t, just like we would expect. And then the second one will be y2 equals t e to the negative 1/2 t. So we want to show that if there's a single repeated root for a second order homogeneous differential equation, that the second linearly independent solution is going to be the same as the first one, just with the independent variable multiplied by it. So we want to state that specifically, and we'll show that that's always going to work. So if r is a repeated root to the characteristic equation for ay double prime plus by prime plus cy equals 0, then y2 equals t times y1, and where y1 is e to the rt. So we want to check and show that this will work. So we're going to plug it in to the differential equation here. We're going to get I need the derivatives first. y2 prime equals the derivative of the first times the second is e to the rt, plus the first, which is t, times the derivative of the second, will give us an r in front of that, rt e to the rt in total. And then y2 double prime equals r e to the rt plus the derivative of the first here is going to be r times the second, e to the rt, plus the first times the derivative of the second is going to be r squared t e to the rt. And then I'll combine these so that this is 2r e to the rt plus r squared t e to the rt. Let's take a look what happens when we plug these into that differential equation. We're going to get a times 2r e to the rt plus r squared t e to the rt plus b times y prime. Let's do some color work here. So y2 is here. Let's make this blue along with this. There we go. And now I'm going to make y2 prime red, write y2 prime in here, e to the rt plus rt e to the rt. I hope that helps you see it a little bit better there. We're going to go plus c, and let's do purple. So y2, we'll do in purple, and we'll say, okay, t e to the rt. We want to ask, does this all equal 0? Is this going to work? And so if we take this and do some rearranging here, we are going to get 2 for a times, how do I want to organize this? 2ar plus b e to the rt. And then we're going to get plus, we want the t terms. We have ar squared t, actually I'm going to put the t after, plus br plus c t e to the rt equals 0. Now, as we look at this, we want to say, okay, is this actually a solution? Is this going to work, generally speaking? And the second part's actually the easier part here. So if I look at this, this is the characteristic equation, and we know that the r value we've chosen gives us 0 for that characteristic equation. That's what it means for the r value to be a solution to that. So that should be 0 since r is a solution to ar squared plus br plus c equals 0, the characteristic equation. Now, the harder part for this is to find out why does this equal 0, because this does work, so this should equal 0 somehow. So how we note this is in the following way. If r is a repeated root, to ar squared plus br plus c equals 0, then this only occurs when r equals negative b over 2a. That is, generally speaking, the general solution to any, if I have ar squared plus br plus c equals 0, then the quadratic formula tells us that r equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we only have one solution here if the discriminant is 0 when we have a repeated root. So if our solution is negative b over 2a, and we plug that in, then we get 2a times negative b over 2a plus b. This equals, oops, I didn't mean to put that parentheses there. The 2a's cancel, I get negative b plus b equals 0. And so yes, we have 0 equals 0, so this is a solution. And we also see that it only works, we can only plug that t in front if the r value is repeated. Otherwise, that first piece that we just saw right here wouldn't end up being 0 if r wasn't a repeated root. All right, one other thing to say about this is that we note also that y1 equals e to the rt and y2 equals t e to the rt are not scalar multiples of each other. I couldn't multiply y1 by just some constant, like 2 or 5 or whatever, and have it be the exact same graph as y2. So these are linearly independent, which is what we need for a general solution. Linearly independent. So the general solution is going to be c1 e to the rt plus c2 t e to the rt. All right, so now we can go back and we see that y1 and y2 are y1 equals e to the negative 1/2 t, and y2 should be then t e to the negative 1/2 t. And our general solution is c1 e to the negative 1/2 t plus c2 e to the, t e to the negative 1/2 t. And as one final note here, I will say that just an abbreviation of all the explanation that I did over here is, if we have a repeated root, then y1 equals e to the rt, y2 will equal t e to the rt, and the general solution will equal c1 e to the rt plus c2 t e to the rt. So in practice, it's really just that simple. Everything else we went over here is explanation showing that that does work and why it works and when it works. All right. Thank you much. And after this, we're going to start looking at how to find particular solutions given initial conditions. Thanks, guys. We'll see you on the next one.